Okay, good morning. I was warned it's a bit glary here. I brought my sunglasses. I just need a guitar and an amp, and we can do this. I think it's not too. It's not too bad. Not too bad. Okay, I've prepared a few notes, and we'll see what happens. We'll see where we go. But yes, as we kind of touched on there in that outline, for me, I've got kind of four key areas that we're going to spend a bit of time on and focus on. We'll start with a little bit general on soil health and just some of that background and some thoughts on soil health. Then we'll move into specifically a little on the soil biology side. And from there, we'll talk, as the topic said, on growing microbes and just some of the ways in which we can grow microbes. And I'm going to talk a little bit about the two different schools of thought. Do we feed the native organisms, or is there a role for introducing new organisms? We'll just try and tackle this debate a little bit. And then we'll round it off with, some of the discussion on the plant microbiome, particularly on the role of the seed. The seed, of course, is all about the future, so there's our link. So, soil health, if we think about somewhat of a historical context, the soil health is somewhat, as you all are aware, somewhat of a term that has gained some current traction. It seems to be very popular these days in the last decade or so. But if we look back historically, there were other terms that were much more pronounced typically. And so actually one of the words was soil fertility. If we look back into a lot of the old farming books, and even somewhat more recently, we had this notion of soil fertility, and of course referring to how fertile the soil is. And fertility generally seemed to have more of a connotation to the chemistry, to the nutritional fertility, the chemical fertility of the soil. This is generally how it was, the meaning that was kind of coupled to this word, fertility. So that was kind of where we all would talk about the use of fertilizers, of course, to improve fertility, organic amendments, or the use of green manures, because, of course, the term green manures was much more of a common term than cover crops as we also have and see today. So we have this idea of fertility was much more of a common word, and over time that really morphed into this then the term of soil quality. And in a way, quality is also quite a broad term, and it overlaps very much with soil health. I mean, all of these terms are quite interchangeable, of course, and there's a lot of overlap. But quality was also more of just a master term, a general term about soil function, soil quality. And it did come with a certain sense of the soil physical aspects, the structure. The quality from the structural point of view, and therefore the function, the oxygen that can get into that soil, and the function that then can come from that. And so we kind of saw more of a transition into soil quality. And if we look into the academic literature amongst scientists and academia in the literature, the word soil quality was also much more used in those circles. And really then the word soil health has emerged, I think, much more recently, much more farmer-driven, ground level, ground up kind of movement, where we have now used this term to also describe a very broad church of things. And it's funny, I see this as an element of criticism around soil health. Oh, it's too much of a fuzzy word. It's not well enough defined. It can mean too many different things. And that is absolutely true. It's a very subjective term. How do we define soil health? What do you define as soil health on one farm, which may be a grazing farm, for example, which we're trying to achieve very different purposes and goals? Versus a cropping farm, where this definition of the soil health might then be, the context might be very different. So soil health is a very subjective term, and even beyond that, it really depends on what is the purpose of the soil. Is it even for agricultural production at all? Soil health could be very different if we're talking about a forestry ecosystem or even a natural ecosystem. The expectation of soil, what we demand of soil, is very different in native landscapes, wild landscapes, natural ecosystems versus our productive areas. So indeed, there's context there. And therefore that context brings with it some subjectivity, and each to their own. We're all different. We all look at different things. When we could all go and dig up the soil. Okay, I'm a big fan of smelling the soil as this kind of broad indicator of soil health. Does it have a nice soil smell? Well, how do we define that? I mean, does it have this nice earthy, kind of mushroomy type smell? Can we smell carbon and litter? Can we smell organic debris, cycling? Does it have the smell of decay, therefore the smell of life? But what my nose smells is going to be very different to perhaps what you all smell and maybe what we see. So it has a certain subjectivity about it, which some people don't like and becomes this fuzzy term. But for me, I see it a little bit the other way. I think that's great. I think that adds to the nuance of the concept. It's not this black and white thing. It does not have to be one thing and one thing only. That it has this nice element of context there. But I think the key thing when we talk, if we transition through this fertility to quality to health, when we talk about health, now here's the operative word here, health. Is it too early in the talk to ask you a question? Am I going to test your comfort levels here? If I say the word health, immediately what is the opposite? What do we think is the opposite of that word? What comes to mind? Sickness. There we go. Sickness. So when we talk about soil health, we have to interchangeably, a bit of yin and yang here, think about, well, soil sickness. It doesn't quite have the same ring to it, does it? But of course, we could define it as poor soil health. The soil health is not very good. Therefore, is the soil sick? Maybe. The word is a bit of a clumsy word in that sense, but nonetheless, there's an important dynamic between those two terms. And when we talk about both of these two terms, health and sickness, of course, we're really talking about something that has to be living. We're not talking about the soil, the health of the nutrients, the sickness of the structure. Health and sickness, it is interchangeably, it interplugs into life, into living, therefore into soil biology. So it is this also thrust into soil biology that you're all aware, that we're a lot of interest in the concepts of soil biology and how we manage soil biology, how we can improve soil biology, improve the life in the soil. I also think these two things, the soil health movement and this traction into soil biology in recent years, these two things go hand in hand. I think if we use terms like health, we really have to talk about biology. And so with biology comes all of that underground world, which I'm only going to actually touch on. We're going to talk more about the plant microbiology, the plant biology a bit at the end of the talk here. But, the soil biology underground, you're all aware. I'm not going to go into that. It's all of those microorganisms, the bacteria, the fungi, the protozoa, nematodes, and we creep onwards and upwards there through that soil food web into some of the smaller insects, into the larger insects, onwards to the earthworms and the birds and the larger animals, and all of life as we know it that exists on terrestrial ecosystems. At the base of that is the soil food web, is the soil, and it feeds and sustains all life on terrestrial Earth. So, of course, then if we think about life and feeding and nurturing this ecosystem, then that word there, feed, okay, if we're talking about feeding the soil, well, then we start to automatically think about things like, okay, compost, manures, these organic amendments. It's about carbon, isn't it? It's about putting carbon into the soil. This is what all of those living organisms like to feed on. Those microorganisms will feed on that carbon, and then all of those larger organisms will feed on the microorganisms, and thus there flows the soil food web. So when we talk about feeding the soil, it's about carbon, compost, manures, green manures, as I said, in that traditional use of that term, or cover crops, as we also may call it now. And so again, it's that kind of dynamic of words here when we talk about feeding the soil, feeding life. What are we feeding life with? What are we feeding the soil biology with? And again, it doesn't quite have the same ring to it, but we're really talking about soil death, soil decay. It is the decay process, it's the decay of manure and organic matter and compost and cover crops, green manures. It is the death and decay of these materials that, of course, brings life. So we have this other little contrast there between death and decay. And somehow hashtag soil death doesn't quite have the same ring to it, does it? So we see much more on soil life and soil biology, etc. But nonetheless, of course, that's that beautiful notion. And we've all heard this before, this idea that, of course, those microorganisms, particularly the fungus, they feed on the death and the decay, and they bring new life. And it's that beautiful notion that perhaps we should all take as we move to old age and perhaps nearer to our time. We perhaps shouldn't be quite so scared of that because with our death and decay, we will bring new life. And, of course, that's that very beautiful notion. Perhaps not something to be quite so scared of. So feeding the soil, it's about those organic amendments. And however, I think what's really interesting, another kind of different paradigm or tension that we see emerging right now is this idea of feeding the soil and making healthy soil. We want to get our soil healthy. We want to optimize soil health in order so that we can grow healthy plants, so that our plants will be healthy. So we have this bottom-up paradigm. And this one is one, for me personally, it's very dear to my own heart. I don't actually come from a farming background. I got into agriculture and this whole career and passion of mine through growing vegetables. I got into growing vegetables when I was a teenager, 14 or 15 or so. And when I started growing vegetables, I just really enjoyed the garden. I started making compost. I thought compost was really cool. So immediately I had this attraction to microorganisms, biology, because I just thought that compost was the coolest thing on earth. And through getting interested in growing vegetables and beautiful flavors and taste that comes with kind of kitchen gardens and taking that food straight into the kitchen and cooking it straight away, all of that pleasure that comes with that. Through that hobby of mine, weekend hobby, I took a great interest in soil. And by the time I finished school, I knew I wanted to go and study soil. And so I went and studied agricultural science. And at that time, I started off growing organically. It was made sense to me. I grew vegetables in the garden myself. I took them into the kitchen. It made sense to grow organically to me. Very much so. So I come from that background, and one of the classic kind of quotes or sayings in the organic world that I've always been held very dear to was this classic line of, "Feed your soil and it will feed you." And I'm sure you've all heard of this one. And of course, I've got a fridge magnet of that exact quote on my fridge. And again, it brings that sentiment of soil care. You know, we must take care of the soil. We must feed the soil. And when we take care of the soil, when we feed that soil, it will feed us. And I think that kind of idea, that mantra, really quite strongly is strongly rooted in the organic world. It's kind of a core kind of philosophy of organic production, historically speaking. And I think what's so interesting at the moment as this new kind of different paradigm is emerging, very much associated with regenerative agriculture, is it's a somewhat of a different view. It's somewhat more of a top-down approach, not this bottom-up approach, let's get the soil healthy and then we will make healthy plants. We have this idea of the use of cover crops, typically strongly associated, where, well, indeed, plants, as they grow into the soil, as their roots penetrate, as they release those root exudates, as the plants photosynthesize and feed those microorganisms, and therefore feed the soil biology, we have this slightly top-down approach of saying, well, actually, I can use plants to improve my soil. It's not about soil feeding the plants. I'm going to use plants and photosynthesis, and therefore those roots and root exudates, to actually change the soil chemistry, change the soil biology, change the soil physics, and influence, therefore, the soil health. So we have this slightly more top-down approach, which I think is fascinating. It just brings that other dimension. And our dear friend Steve Kenyon here in the audience has that also very beautiful quote of his, modern agriculture grows plants from soil, regenerative agriculture grows soil from plants. So it's this idea that, well, now we're really trying to use plants and manage plants, be that plant diversity or plant nutrition or plant health, and then through optimizing plant health and plant growth and plant biomass and those roots, well, actually, we can change and we can indeed improve soil health. And that's these two very different kind of schools of thought, very complementary, of course, very much so, but also very different. And it brings in this element into the discussion about life and the role of biology in forming soil, in making soil, the role of biology. And when I say biology here, I mean the role of plants, plant biology, photosynthesis, and the microbes that associate with them, the role of biology in making soil. And to quote our other good friend, Ray Archuleta, soil without biology is just geology. And that's absolutely valid. That also encapsulates this essence of, well, if plants weren't there, if we didn't have plants, we didn't have microbes, we would just have parent material. We would have rock. We would have rubble. We would have parent material. And it is the action of plants, photosynthesis, depositing carbon into that parent material, into that geology, that then we begin to form soil. That is the process of soil formation. So, of course, therefore, soil biology, our biology broadly, is indeed central in making soil. This is why on Mars and on the Moon, we just have geology. We don't have soil there. We don't have life. We don't have the interaction of biology. So it is biology itself that actually makes soil. But then it is, of course, biology that is influenced by the health of that soil or the function or the quality of that soil. So I think it's really fascinating, that dynamic between those two different paradigms, very complementary, but also somewhat different, of this top-down, bottom-up kind of approach. And so I think that when we think about how those plant roots, how they change the soil, how they feed the soil, it's really quite a remarkable story, an example. Actually, most of the microorganisms, anyway, in soils are dormant for any given moment in time. They're all pretty much asleep and dormant. It is the action of that plant root that begins to germinate and from the seed and penetrate down into the soil. It is the action of that root and those root exudates, the sugars and carbohydrates and oils and all sorts of other compounds that are leaked out into the soil, that then wakes up the soil biology, activates the soil biology. They become awoken from those sugars, from that carbon, from that energy that is excreted out of the roots from those root exudates. And it's really quite a remarkable story. I mean, in a very, very tiny, minute spatial gap between the plant root and where those root exudates are leaking out, to only just a few millimeters away, we then have the bulk soil, which hasn't received any of these leaky root exudates yet. Literally millimeters away, we will have vastly different microbial communities functioning. The plant releases those sugars and exudates to wake up, to activate all of the dormant organisms from the bulk soil. All those they're there, but most of them are asleep, waiting to be activated from those root exudates. So in such a tiny spatial gradient, we can see multiple-fold increases in microbial activity, 100-fold more microbial activity 2 millimeters away from there to there. It's extraordinary. And so I think that kind of example really illustrates this role of the top-down, or the role of the plants in driving soil health, because the plants are activating those organisms to such an extent, to such an incredible extent, in which then overall that interaction changes the soil, improves soil health. But again, we don't want to be too one-sided. It's always a two-way street. Life is full of give and take. And of course, the organisms in that soil do still also influence plants. It's not all that plants are the drivers, and plants and roots and root exudates. It's not that they're doing everything. There is a two-way street. Of course, the microorganisms and other organisms in the soil, of course, they are cycling nutrients. They are feeding on the organic materials, they're spitting out their waste products, excreting, and they are cycling nutrients. And if they were not cycling those nutrients for the plant would not be able to access those anywhere as efficiently. So, of course, the microbes are also working in tandem. And if we look at then some topics like seed germination or breaking dormancy in the seed, indeed, the microorganisms particularly have a very important role in breaking seed dormancy and in encouraging germination. So the bacteria, the fungi, as they grow and die and do their thing in the soil, they're also excreting all sorts of byproducts, kind of various, sometimes waste products and compounds, microbial exudates of their own, microbial metabolites, various byproducts. And some of those microbial byproducts can be compounds, bioactive compounds that can suppress germination or trigger germination of the plant. So there is also this two-way street where the microbes do, for sure, the soil biology does, for sure, also influence plants and plant development and plant growth. So again, I think it's this beautiful two-way street here that is always important to see the view from both sides. It's very important in all aspects of our society. So it is a two-way street. And then, so if we then move on to part of the topic that was given for today, growing microbes, how can we grow microbes? And there immediately we must hit this, again, debate between, do I simply feed the organisms who are already there in the soil, feed the native organisms, they're clearly there, they're functioning already, they're adapt to growing in this soil. Do I just simply feed those and encourage those? Or is there scope for introducing new populations, the use of microbial inoculants, introducing new microbes into the system? And indeed, for me personally, there's no right or wrong to that answer. For me, it's a combination of both. I think both have a role. Now, there are some concerns on both sides. I see there's this discussion about, well, we must be careful about introducing new microbes into the soil. They could end up being aliens. They could take over in that soil. They could induce dysbiosis, some kind of imbalance in that various those communities. So there's, and rightly so, we've seen this, of course, with plants who take weeds, who become weedy and take over, and other animals. Of course, this is a real problem of introduced species causing ecological disturbance and all sorts of problems. So, of course, that is a real concern. And I think at a microbial level, perhaps that is even, for some, even more concerning, because we can't see what's happening. It may be happening at this microbial level. So I think this is a very valid point to make, and something we should be cautious and mindful of. However, we could also ask the question, well, does this happen in nature? Does it happen naturally that microbes are introduced into new landscapes, into new soils? And indeed, the answer to that is yes. We are introducing microbes into soils all the time. We do it through the application of manures, through the application of compost. Of course, these materials are living, they are biofertilizers, they are living fertilizers. So when we apply these organic amendments, typically we think about them when we're applying some organic matter, and that's good for structure and feeding the biology, which it does. We're applying these things to supply nutrients for feeding the plant, and indeed they do. But we are also introducing microorganisms. So there's that side of it that happens quite normally, naturally. No one gives two thoughts about the application of compost or manures. We would automatically say, well, that's a good practice for soil health. This is a good thing to be doing. We don't normally flag this concern around introducing some foreign species. But the other one, which we're going to come to and talk at the end, is then about the seed itself. And I don't want to spoil the surprise before we get there, but when we plant seeds, indeed the seed itself is a microbial inoculant. There are microbes that live on and in that seed. So when we put that seed down into the soil, we are introducing microbes into the soil. And of course, we've been trading seeds as human culture for many hundreds and thousands of years. We have been trading and moving seeds around. So arguably the horse has already bolted from the cart. Indeed, we've been trading seeds. Indeed, we have already been moving microbes around into different soils. And indeed, that has come with some costs and some problems. There have been examples of that being problematic. But again, if we think about a natural ecosystem, that is the process. So the seed is the process of colonization. It's how the plants will spread. It's how they will colonize. It's how they will cover bare earth and disturbed parent material or soils and grow weeds and start that succession and cover it up and grow. So seeds are supposed to move into new environments. That's what they do. That's what they've done for a very long time on planet Earth. And so there is an element or an argument there that we could say, well, this is somewhat of a natural process that perhaps we could be facilitating or optimizing. So again, I can't help but look at these situations and think there's two sides to this coin. There's some good arguments on one hand and some good arguments on the other. I don't think that there's necessarily a right or wrong. I think there's scope for both. It's about integrating what's relevant and applicable for you and your system. Now, in that debate, however, I do put a hierarchy. I personally would say, well, of course, it has to make sense. It makes more sense. It has to make sense that we should start with feeding the natives, just nurturing who's already there. They're clearly already there. They clearly adapt to your soil, to your environment, to your conditions. they're clearly thriving already. How about we just support them and nurture them? So, that opens then that discussion of feeding the soil. How do we just feed them? How do we nurture them? And of course, the answer to that ultimately comes down to carbon. It's about putting carbon into the soil. That is what is going to feed the native organisms and support them. Now we can put carbon into the soil through the use of plants, through the use of that photosynthesis and those roots and root exudates that we talked about briefly earlier. And so we do that through cash cropping. We are feeding the soil and we cash crop. We do that through cover crops or green manures. We are growing plants and then leaving those roots and exudates, or integrating the green manure, clover plow down, or whatever it might be, integrating this material into the soil to feed the soil. So plant biomass can go into the soil. That provides carbon. Of course, we have compost and manures, as I touched on already, and a range of other organic amendments. We could go on and on there. Or crop residues, for example, of our stubbles and residues that we can also leave behind. So ultimately, these are carbon inputs, and it is carbon that is going to feed the soil. So that's one part of the puzzle. Let's just feed them with those various carbon-based inputs. From there, we could use other things and other strategies too, like liquid options, things like molasses. I see people using a lot now, fish hydrolysates, these kinds of things, seaweeds and kelp extracts. They bring some of these important trace minerals and some other benefits to use materials like that. And other things like humic or fulvic acids, these types of things that some of you may have come across. So ultimately, again, be that in a liquid form, be that in a dry form, ultimately they're all carbon compounds, and it's carbon in which we are feeding the life in the soil. Now, when we then move to the discussion on the other half of using inoculants, I think that, our starting point, where we should begin, where we should always focus our strategies, as I say, is feeding the natives with those carbon-based inputs. But there may be instances where an inoculant can be beneficial, a microbial introduction can be beneficial. Now, again, within that side of the debate, I have a hierarchy. I would say that, well, if we are going to be introducing microbes into the soil, the first and foremost strategy should be DIY inoculants, microbes produced already on farm, again, in your native environment, in your localized microclimate, etc. So here I'm talking about making your own compost on your farm. Again, you're culturing microbes from the locality who are going to, therefore, more likely to thrive and colonize in your soil. So if we are introducing new microbes, it should be ones that we are making on farm. So there's compost if you're making it on farm. There's your manures, cycling of the animal material, etc. So those are the ones. And then we have all sorts of the other ones that kind of spin off from there, things like compost teas or compost extracts. And again, you should be, if you're going to be using those, ideally using them from compost you've made on farm. And then some of those other fermentative types of microbial products. I see a lot of these anaerobic or fermentative types, so kind of brewing up without oxygen, but more of a fermentation style, these kind of biofertilizers where we can take all sorts of materials. It could be spent plant materials, but other mineral components, and do almost like a lactobacillus ferment. It's almost like kind of making a yogurt type thing. And so we can kind of do these cultured microbial brews, again, made from ingredients, raw materials that perhaps you are sourcing from your farm or fairly locally as you can, and then making those ferments or those cultures, microbial cultures, making them on farm. So I think those are a good middle ground also between this debate of, well, do I feed the soil or do I introduce new populations? Here's a nice middle ground, says, well, if we're going to introduce new populations, let's make these microbes ourselves in our locality from local ingredients, etc. So that would be where I would start. Now, then the area where this is most then hotly debated is this idea of using commercial products or lab-based cultures of microbes that were cultured in a lab, dried out into a dormant product that we can rehydrate and apply onto the soil or onto the plant, etc. So that's typically the one that I would also put at the bottom of the rung in terms of that priority. And this is typically the one that is also more hotly debated amongst those that are against the idea of introducing new microbes. And part of that reason is that when a manufacturer would produce and commercialize a microbial product of some kind, of course, they're going to want it to be effective. So they're going to be choosing varieties, species, or strains of those microbes, which are like varieties, but in the microbe world, a strain of a particular species. They're going to be choosing strains who are very robust, who have a broad array of applicability, a broad array of conditions. So, for example, a particular strain that can tolerate acid or alkaline conditions, so that when the end user, depending on their soil type, if we have more acid or alkaline soil type, that this product will actually function and thrive. As we're all rightly concerned about some of these products, sometimes they can be very expensive and sometimes not very effective, because if we introduce a microbe into the wrong environment, obviously it's not going to function. So when we look at some of those lab-based products, typically they will be selecting strains who are very hardy, who have a wide tolerance of applicability, of adaptability to where they will thrive. And even beyond that, sometimes within those cultures, they will often be kind of bombarding those with different stresses to actually build up the tolerance. So kind of intentionally stress the strains with salty conditions, or again acid or alkaline kind of different conditions, to actually build up the tolerance over generations, so that the strain becomes more adapted to those difficult conditions. So you have this somewhat of a super microbe being kind of cultured there, which then, yes, increases the chances that it will be effective when used, and not just a waste of time and money, but comes then somewhat with that risk that it may be more adapted to then come in and occupy a stronger ecological niche and cause some disturbance within the native community. So that's kind of the argument there. And however, that said, I think that in some instances there can be a place for these products. We can use very specialist microbes. The beautiful thing about microbes in the soil, they exist in incredible diversity. And therefore, with such diversity comes such diversity of potential functions that they can bring. So we have all of those nitrogen-fixing bacteria. You'd all know the ones who associate with legumes, our rhizobium, but there are many other free-living bacteria who fix nitrogen, who can associate with any plant species at all, associate with those roots, feed off those root exudates, and fix nitrogen in return. Some of those nitrogen fixers can even live inside the plant. And these are called endophytes, where they can also fix nitrogen out of the air into the plant from within the plant. And we'll talk briefly on those when we get to our final section here in a minute. But then we also have other specialized functions in these microbes. They can suppress very specific diseases. So they can be biofungicides, and this, of course, we're all concerned about the overuse and over-application of some of our plant protection products, pesticides, etc. So we have a range of potential bio-alternatives. A biofungicide, a fungus that eats other fungus, and it can control that disease through that natural kind of predation. So we have very kind of targeted functions like that, microbes that control insects, other bacteria that solubilize phosphorus, make nutrients available, all of these kinds of things that I'm sure you've heard about before. So therefore, these very highly specialized and targeted organisms can also then sit within a broader systems approach, an integrated approach where, okay, if you are specifically needing some extra nitrogen for a nitrogen-hungry crop, okay, that inoculant, that specialized inoculant is probably going to do the job better than a generalized inoculant made from some compost extract, for example. So you have that level of targeted kind of rifle kind of specificity, targeted approach for specific outcomes or specific functions. So that's where they can also indeed play a role. But again, as I summarize, I think my order of preference is still we feed the natives, we culture our own microbes, and we use some of those targeted and specific products as our kind of third line of defense. And I personally believe that an integrated approach of all of those is generally going to be a very good strategy forward. Okay, so that leads us to then our final section, and I will just waffle on for as long as I can, and then I think maybe we'll just take some questions and have a bit of a discussion, so we can hear what kind of things you guys want to hear about. I can gauge what you're interested in learning about, and we'll try and have a bit of a discussion through some questions, just to kind of maybe bring some context to my thoughts into your farms and your systems. So we move into this final section here on talking about the plant, what's called the plant microbiome, or often called the phytobiome. So this is referring to all of the community of organisms who live on or in the plant, highly, strongly associated with the plant. So these are not necessarily the organisms that live in the soil. We often hear that term, the soil microbiome, soil biology, etc. Well, indeed, we have a whole group of microbes and other organisms who associate specifically with the plant. Now, that can be on the roots or in the roots. That could be on the shoots or in the shoots. That could be on the leaves or in the leaves. That could be on the flowers or in the flowers. That could be on the seed or in the seed. They associate in all range of plant organs and plant in these microhabitats of the plant, stems, leaves, absolutely everywhere, you name it. And of course, the seed is the one I will come to and want to focus on, and it has that link to our discussion just earlier that the seed itself is that vector for introducing new biology into new ecosystems, into new terrains. There is that link there into that debate. But before we kind of go there, it's just to say that this is very much an emerging area of the plant sciences, the understanding this plant microbiome. We've spent a lot of time and attention looking at the soil biology, the soil microbes, and now we have, okay, very quickly, we have learned how complex that is. It is just a vast and complex underground world, thousands and thousands of different species, billions and billions of actual numbers of organisms. It's just such a complex and entangled web that we are trying to unpack, and we're getting much better at that with some of the modern tools that we use now, some of the genetic and molecular tools that we can kind of peer into the soil and actually see the vast genetic diversity that exists there in soils. But with that complexity, of course, comes time and difficulties in studying that. It's a very difficult system to, of course, study. And so some aspects or some areas of the research has now moved into the plant microbiome because it's I use this word a little bit carefully, but it's a little less complex. It's a little easier to study. I say that very tentatively. The plant microbiome is still a very complex world, but why I say that is that in soils we have huge numbers of diversity of organisms, but when we focus in on the plant microbiome, we narrow that diversity significantly. There's nowhere near the amount of, there's still very diverse organisms, but nowhere near to the extent of what we see in the soil microbiome. It's a very small fraction. And indeed, that's where the plant microbiome comes from. The plant actually is taking from, it's borrowing those microorganisms from the soil, which ultimately colonize the plant and colonize those leaves and stems and flowers and fruits and roots. Those organisms come from the soil. The plant recruits them. It through those root exudates and leaf exudates and other smells and scents, volatile organic compounds, a whole range of different modes and mechanisms in which it does this. But the plant is actively recruiting or suppressing, keeping away microbes from that soil, or recruiting the ones that it wants. And then those microbes can, for example, enter the root. They can travel throughout the plant and go up to the leaves, up to the above ground biomass, or to the flowers, and etc. So the point is that most of those microbes actually come from the soil. And those organisms that come from the soil, this is something referred to as horizontal transmission, meaning that the plant gets those microbes from its local environment, from the soil, sometimes from the air. I mean, they can blow in through the air as well. There is an air microbiome. So sometimes organisms do come from the air and colonize the plant. But typically, most of them come from the soil, and this is referred to as horizontal transmission, acquiring these organisms from the local environment. And we're just beginning to understand what they do. The well-studied one is those organisms that live around the roots. This is called the rhizosphere, and this is those many millions of microbes that will crowd around that plant root system and feed off those root exudates, become active, be recruited, become active, and then perform those various functions. So that's the one that's been fairly well studied, and that's the one that's really important for cycling nutrients, getting nutrients out of the soil, delivering them to the plant in available forms that ultimately helps plant growth. But as we move onwards into the root and upwards into the above ground biomass, indeed, we have these communities, very specific and unique groups of microbes, and it's usually when we move above ground and talk about the above ground parts of the plant, it's dominated by bacteria. We do see some fungal organisms up in the plant above ground biome. We do even see some protozoa and some nematodes, much less. They're mostly down in the soil. So it is primarily bacteria and fungi who do exist above ground, but it is dominated by bacteria. It is mostly bacteria who we will find in the above ground parts of the plant. And as you might think, as we might or assume or generalize, some of those bacteria that live on the leaf and in the leaf, they perform various functions that ultimately help with photosynthesis. We see some of the microbes that associate with the flowers. Ultimately, they can help with pollination type processes, ensuring that pollination kind of is adequate, is achieved. And of course, as we'll talk about, the microbes associated with the seed, they're important also for the next generation. That'll be our link to the future part of the talk. So we're just beginning to understand that the microbes that live in these different microhabitats of the plant, they do perform very specific functions, and they have very specific, they are localized, or they will colonize, they will grow uniquely in those regions of the plant. The plant seems to recruit them from the soil. They're sent to the leaf or to the stem or the branch or to the flower, etc., where they perform their various functions for the plant. And I mean, the flower microbiome is a very interesting one. This is one that we know a lot less about. It's a very interesting community of organisms that grow on the flowers. It turns out that some of those, again, mostly bacteria that live on the flowers, they actually will use the floral scents. So when we talk about smells, flower smells and scents that we enjoy, that we smell, those compounds that we are smelling, they are called volatile organic compounds. Volatile meaning they can off-gas. They turn into a gas, drift off into the air, hence we can smell them. It turns out that some of the microbes that live on the flowers actually use those smells, those volatile organic compounds, as a food source for themselves. It's how they grow their bodies. They capture those, they digest them, and they feed on them, and they grow their bodies. It also, again, one of these wonderful examples of the two-way street, it turns out that those very same bacteria on the flowers also induce changes in the floral scents. So the bacteria actually are inducing changes in smells and scents. So they've done some fascinating studies of growing plants in sterile, growing flowers, plants and flowers in sterile lab conditions, and the plants don't have smells, or they have very different smells. So those bacteria that live on there are actually two-way street. They're feeding on those smells and scents, but they are also inducing unique changes to those floral scents. So perhaps an opportunity there for the cut flower industry to optimize some of those kind of processes that we are still indeed untangling. But the flower microbiome becomes another layer of trickiness beyond there, and it also, therefore, has some complexities about studying it, which makes it also very interesting, is that flowers, of course, are highly, highly attractive microenvironments. We're all attracted to them. We can see them. They catch our eye. They catch our nose. We are attracted to them, and we have a smell. Of course, the insect world is also very much so. So that's the point of the flower, of course, to attract in the insects, the pollinators, etc., to help the plant perform that function of pollination. So, of course, when we then move into the insect world, just like plants that have their own plant microbiome or phytomicrobiome, the microbes that live all on and in the plant, well, of course, so do insects. Insects are covered in what's called an insect-associated microbiome. So the insect has microbes all over it. of course, just like we do. We have microbes all over our hands, all over our bodies, and of course inside our bodies as well. So all organisms do. Indeed, we could argue that it is the microbes who are the rulers of this planet we call Earth, but they're the ones really secretly in control, I think. But so there is an insect-associated microbiome. So of course, when an insect visits a flower, it will leave a fingerprint of its insect microbiome on that flower. So that's very interesting, because now we're also looking at studying the insect microbiome on flowers, and it can tell us which insects have been visiting. It gives us some kind of indication of a broader ecosystem services and functionality of which different types of pollinators or insect species, etc., are visiting those flowers. They leave that fingerprint there. They leave an imprint of their insect microbiome as they go about their day, which of course then also interacts with that flower microbiome, with the plant microbiome. One, adding another layer of complexity for us to study these, but also opening some fascinating windows and doors into understanding a broader ecological function of this interaction. So I think the flower one is a very interesting one that we will follow with interest. And then really, of course, once the plant is flowering, I talk a lot with my hands. There's a reason I like the lapel microphones that give me freedom to talk like an Italian, but I must have been Italian in a former life. But okay, so of course, from the flower comes the seed. And again, the seed then is an interesting one in terms of the biome that exists in and on that seed. Now, I talked about this just earlier, that the plant acquires the microbes from the environment, acquires them from the soil, this being called horizontal transmission of that biome. Well, there's another pathway, another mechanism by which plants acquire biome, and this is what's called the vertical transmission. And this is the one that I'm referring to, is referred to through the seed. And what that really means is that the seed microbiome, when the plant flowers and produces that fruit or grain or whatever it might be, as that seed is ripening and maturing, actually the plant will be sending very specific microbes, sometimes from the leaf, from the stem, from the roots. It's very specific, and only some species of these microbes will actually travel up internally and get into that seed as the seed is forming. So they have then again colonized the inside of that seed. So when that seed then matures and blows off in the wind and goes off and does its thing to go and colonize, or if we harvest it, of course, that then is a selection of microbes that are now existing in and on that seed, which then has come from the mother plant. And so this is what's called this vertical transmission, or inherited transmission, inherited microbiome that comes from the mother. Now, what's fascinating about this pathway is that microbiome that comes from the mother plant, this vertical transmission, it is unique for each and every species, be that a tomato versus a wheat, or versus a grapevine, or versus anything. It is unique to that plant species. And indeed, if it's not just unique to that environment, the tomato microbiome in that seed grown on another part of the world can also have commonalities. It is unique to that species. And this is called a core microbiome. It's the groups of microbes that are consistent to a plant species irrespective of the environment in which it's grown. So these are, again, we're narrowing the number of organisms that are relevant here. It's just a smaller number that come from the vast diversity of the soil. It gets narrowed into the plant and gets narrowed into the seed, narrowed specifically for that species. And this is called a core microbiome. And all tomato plants, or all wheat, or all spelt, or anything, these are common. They have this in common. And so we begin to understand, okay, well, these organisms must be very important for that specific species. And what we now are beginning to understand is what do they do? Okay, they're obviously important because they're being inherited vertically. They're being inherited from the mother. The mother has put them there for a reason. They clearly are performing some very important function if they have this in common with all tomatoes, etc., around the planet. When that seed is planted, be that naturally, a natural ecosystem drifts off into the air, or when we plant that seed, what we now are beginning to understand is that seed microbiome is critically important to the germination and establishment process. And specifically what it does is that when we plant a seed, the microorganisms that become active immediately, come active first, is those ones in the seed microbiome. This is before the plant has begun that germination process, or just as it's beginning, before that seed starts to absorb water and swell. The seed then begins to release some seed exudates, and then that root emerges, and then we have those root exudates. But before all of that happens, this core microbiome, the seed microbiome, if we could use the analogy, is that they set the table. They are the catalyst. They start the process of helping that seed communicate with the soil microbes. So the ones in the seed, they germinate first, they colonize, they become active first. And what they do, they provide a protective layer around that seed where they start the communication with the organisms in the soil. So they set the table, they set the stage. They are the ones that begin the dialogue with the soil microbiome and say, okay, we don't want all of you, but we do want some of you, and we're going to begin that recruitment process. So it turns out that that's what the seed microbiome does. It establishes the connection between the plant and the soil microbes. They play a very important role in setting up lines of communication, of setting the table there. As the root emerges, then that root gets colonized very quickly by the soil microbiome, and then the soil microbiome absolutely take over. Then they will colonize that plant and become the dominant biome around that plant. But it is that seed microbiome that starts that process, that facilitates that process, is one of the important things that we are beginning to understand that is what they do. So, of course, that's very important because, as we talked about, that we all know soil biology is really important, and we want to facilitate and enhance all of those interactions, and our seed microbiome is going to help us do that, start that process onwards. But again, it's that seed microbiome that is consistent, that core microbiome is consistent across a range of different kind of plant species. So this is also, again, one of the next avenues of helping us maybe be more targeted in the production of some of our microbial lab-based inoculants, because now we can see that, okay, all of the tomatoes or all of the grains or this or that has these specific ones, and we can potentially produce inoculants that are very targeted for that very specific species in order to ensure those organisms are there. Because they may not be there if we have potentially used a seed dressing. So obviously a fungicidal seed dressing, we, again, like classic, we often do, very narrow focused mind. We use some of these inputs to protect the seed from the baddies, from the pathogens. We actually have very little idea on what they may have done to the core microbiome, to that seed microbiome, the beneficial microbes that also exist on and in that seed. We have very little literature on the impacts of some of our seed dressings on those. We can make a strong assumption that there would be some species in that seed microbiome. It's not to say that it would kill them all or nuke them all, but there would be some species who may be compromised. There will be others who won't be compromised. It really is dependent on a kind of case-by-case scenario. But nonetheless, there's definitely an avenue there in which it may be having some very negative effects on that seed microbiome that we had no idea about. We are only just really beginning to understand this whole idea of the seed microbiome and the core microbiome for a species-specific core microbiome in very last few years or so, in the last 5 or maybe 10 years at a push. So these are the things that are really important. And so I think that then I see my time is actually running out quickly all of a sudden. I thought I was going to finish really early, and now all of a sudden I've only got 6 minutes, but that's okay. I'm actually at the end. I think I wanted to just then give a small practical kind of closing to say that, okay, if we acknowledge that the seed microbiome is an important aspect and it's very potentially important for this intergenerational transfer. This then brings to this closing kind of point, or the importance of, in my mind, seed saving. This is kind of the key practical outcome of some of this discussion, is that when you source seed from somewhere else, it opens this question, well, what soil type was that grown on? What microbes did that seed horizontally, what seeds did it acquire from its environment? Because there's a lot that come from the environment and there's some that come from the mother. Both are important. So, of course, when we grow seeds in other soil types or in other parts of the country or other parts of the world even, those seeds have acquired the microbes from that environment, as well as their own core microbiome. But, of course, then we bring that seed and put it into your soil with very different organisms in your soil. There's actually a big question mark. Well, is that actually the best seed or the best variety or the best microbiome for your conditions? And I think this is part of, we typically have associated this idea of, oh, different varieties, or some varieties work well in my soil or not others, etc. But I think part of that discussion perhaps actually could also be the fact that where we source those seeds from might have a microbiome that's not aligned to your own microbes in your soil. So it opens up just the very obvious practical take-home of seed saving. If you grow a seed in your soil and that plant grows and it acquires a biome from your local microclimate, and it has that horizontally transferred plus the vertically one through the mother, and then you replant that seed, well, that seed, of course, last year grew in your microclimate. So it's somewhat already attuned to the organisms that exist in your soil. And so when you replant that seed is already knows how to speak the lingo, can already speak the language of that soil population, and it will better establish and better adapt. And I think when we multiply that through a good couple of generations, I think 4 and 5 years in of seed saving, we can really start to see differences in the performance of that variety. If you went back and sourced that same seed again from a different supplier 5 years on after saving it and put them side by side, I know they're the same variety, they are the same genetics, but there would be some of these environmental or epigenetic type changes that have occurred through that seed saving, and I'm convinced you would see some differences there. So I think, therefore, in closing, the practical kind of take-home there is I would encourage the age-old practice of seed saving that somehow we lost along the way through our progress, that I think we should return to some of those concepts, and I think seed saving could be a really important one, not only from all of that discussion about food security and why it's really important to save seed from a food security point of view, but even from a microbiome and seed biome and therefore plant health point of view. I think this is also something to encourage. So, okay, we'll leave it there. Thank you. If we've got time for a couple of questions, happy to take if we can.
Thank you, Joel. Thank you.